A standard method of solution is a pattern that appears again and again in algorithm questions, and the syllabus limits this to six: totaling, counting, finding a maximum, finding a minimum, linear search, and bubble sort. The reason to learn them as patterns rather than as individual algorithms is that exam questions rarely ask for one in isolation. They give you a scenario, process these exam marks, or handle these temperature readings, and expect you to recognize which patterns are needed and combine them. So, what you are really learning is a small vocabulary. Once you can see that a problem needs a running total, a counter, and a maximum, writing it becomes assembling three familiar shapes rather than inventing something. Totaling accumulates a running sum. Set a variable to 0 before the loop and inside the loop add each value to it. Counting is the same shape with a different body. Set a counter to 0 before the loop and add 1 inside, not the value 1 every time the thing you are counting happens. The two are so similar that they are often confused, so hold the difference clearly. Totaling adds the value, counting adds 1. If a question asks for the total of the marks, you add the mark. If it asks how many students passed, you add 1. And both share the same critical detail, which is where the initialization goes. It must be before the loop. Setting total to 0 inside the loop resets it on every pass, and you end up with only the last value. An error so common the next lesson, but one lists it first. Say the initialization aloud when you write it. Total starts at 0 once before we begin. Finding a maximum, hold a variable for the largest so far, and for each value, if it is greater than the current largest, replace it. Minimum is identical with the comparison reversed, and here is the detail that decides the mark. What do you initialize the largest so far to? Setting it to 0 works only if every value is positive. Give that algorithm a list of temperatures below freezing, and it returns 0, which is not in the list at all. The safe approach is to set it to the first value in the list and then compare from the second onwards. That cannot fail because the answer is guaranteed to be one of the actual values. Average combines two patterns you already have. Total the values, count them, then divide the total by the count after the loop. After, not inside, dividing inside the loop gives you a running average of everything so far, which is a different thing and almost never what was asked. And guard the division. If the count is 0, dividing by it is a runtime error, so an algorithm that might see no data at all needs to check first. One term that comes up alongside these, a rogue value, also called a sentinel, is a value outside the range of valid data used to signal the end of input, entering -1 when all real marks are 0 or above, or the word stop for a list of names. It lets a loop run an unknown number of times. Keep reading until the rogue value appears. 2 points earn marks. The rogue value must be impossible as real data, which is why -1 works for marks and would be useless for temperatures, and it must not be processed. You check for it before adding it to your total, or your total is wrong by exactly -1. That ordering, test, then process is the whole technique. Linear search looks for an item by checking each element in turn from the beginning until it finds a match or reaches the end. That is all it does, and its simplicity is exactly its advantage. The data does not need to be in any order, which matters because sorting first costs more than searching an unsorted list once. Its disadvantage is speed on large lists. In the worst case where the item is last or absent, it checks every single element. 2 implementation points. The search must be able to end in 2 different ways, found and not found, and an algorithm that only handles found will loop past the end of the list. And once the item is found, there is no reason to keep going, so a well-written linear search stops, which is what a flag variable or an early exit is for. Bubble sort is the one method here you cannot really understand from a description, so let us run a pass. The list is 5, 3, 8, 1. The algorithm compares each adjacent pair in turn and swaps them if they are in the wrong order. First comparison, 5 and 3. 5 is greater than 3, so they are in the wrong order. Swap. The list is now 3, 5, 8, 1. Second comparison, and note that we move along by 1 and compare the next adjacent pair, 5 and 8. 5 is less than 8, so they are already in order. No swap. The list is unchanged. Third comparison, 8 and 1. 8 is greater than 1, swap. The list is now 3, 5, 1, 8. That is one complete pass, and look at what it achieved. 8, the largest value, has moved all the way to the end. That is not a coincidence, and it is the point of the algorithm. Once the largest value is reached, every subsequent comparison in that pass moves it one place further right, so a single pass always carries the largest remaining value to its final position, which is why the next pass does not need to check the last element, and why the pass after that can ignore the last two. The list is sorted after at most n-1 passes, and it can be stopped early if a pass completes with no swaps at all, because no swaps means everything is already in order. One detail inside that algorithm deserves attention because it is examined directly. Look at how the swap is written. Temp gets list I, then list I gets list I plus 1, then list I plus 1 gets temp. 3 lines and a temporary variable for something that sounds like it should take one. The reason is that assignment overwrites. If you wrote list I gets list I plus 1 first, the original value of list I is gone, overwritten, and there is nothing left to put into the other position. You would end up with both positions holding the same value. The temporary variable holds one of them safely while the other is moved. If a question asks you to complete or correct a swap, that missing temp is what it is testing, and it is worth being able to say why rather than just remembering the shape. In practice, questions combine these, so here's how to approach one. You are given a list of exam marks and asked to output the total, the average, the highest mark, and how many students passed. Read it as 4 patterns. Total, accumulate. Count, add 1 per student, needed for the average. Highest, initialize to the first mark and compare from the second. Passed, a second counter, incremented only when the mark is 50 or above. All 4 can be done in one pass through the list. You do not need 4 separate loops, and writing 4 is a sign you are treating them as separate problems rather than as patterns sharing a loop. Then after the loop, average equals total divided by count. Notice that 3 initializations go before the loop, 4 things happen inside it, and 1 calculation happens after. That before, inside, after structure is the shape of nearly every algorithm in this topic. 4 things to take into the exam. First, put initializations before the loop and the divide by count after it. Position is where most of the marks in this topic are lost. Second, initialize a maximum to the first value rather than to 0 and be able to say why. 0 fails when all the data is negative. Third, for linear search, give the advantage and the disadvantage in terms of the data. It works on unsorted data, and it is slow on long lists because in the worst case, it checks every element. And fourth, for bubble sort, say that each pass moves the largest remaining value to the end, that a swap needs a temporary variable, and that the sort can stop early if a pass makes no swaps. Those 3 sentences cover almost anything a bubble sort question asks.